Hello, I'm back again and welcome to chapters 3.3 to 3.4. So what we are doing now is to investigate systems of forces. We looked at, in the first discussion, forces in 2D, forces in 3D, equilibrium in 2D, equilibrium in 3D. And then yesterday, we looked at some introduction to moments. So we looked at moments about a point, moments about an axis. The prerequisites to that were vectors. So we studied products of vectors, the vector product and the scalar product. Then we also went through the mixed triple product so that we can find the moment about an axis. Right, so having established all that, was a process to try and explain what happens when we have couples, forces, and systems of forces. Because in reality, we always have a lot of forces that are acting on our objects. Right, so this lecture just covers your couples, systems, and a system of forces, how you can actually reduce to a simple system of forces. So there's a cool project, look out for it close to the end of this lecture. Okay, so we are looking at couples and force couple systems. 3.3 is on couples and force couple systems, and there are 5 principles that guide our understanding or how we need to analyze couples and systems of forces. So we will look at the principle of the moment of a couple. Then we will move to equivalent couples, addition of couples, couple vectors, and resolution into couples. So what is a couple? What is a couple? So a couple is simply a set of 2 forces. These forces are equal in magnitude. These forces are parallel, so their lines of action are parallel, but the forces point in different directions. An example is, this is the best example of your wheel spanner. So for your wheel spanner, for you to undo one of the nuts or bolts, you would need to apply an upward force with your left hand, simultaneously a downward force with your right hand, thereby increasing your your turning effect. So that way you'll find that it's actually easier to unlock those bolts or nuts or lock them using a wheel spanner, which is like this, as compared to the single lever, which is exactly this long, right? So that is what we were studying when we were looking at moments of forces about a point or about an axis. So now, when we have a couple, we can actually find the moment of that couple. Figure 3.26 is an example of a system which has a couple. So in this figure 3.26, we have the origin at O, we have a point at A and another point at B, at which the forces F and minus F are acting. Those 2 forces, they are anti-parallel, right? They are anti-parallel. So if they're anti-parallel, then they form a what? A couple. That couple, the forces are acting at points that are located at RA, the other one is located at B, that is a distance or a position RB from the origin. So if we have a setup as such, one can find the moment of this couple by individually looking at the moments of each force. So you are actually applying which theorem? Do you still remember the theorem? Varinon's theorem. Okay, so this equation here is just explaining that. So it shows us that we can find the moment of the force F, which is a distance RA from the origin. And then we add it to the moment of the force minus F, which is a position RB from the origin. When we add them up, you will notice that this negative sign there, it can move around if it's a cross product. So it can actually end up on this RB, which is the reason why, since F, the vector, is common, we can then factor out that vector and put it out there. In the end, all you have is the relative position, RA minus RB. And if you look at this vector here, it's conveniently located in such a way that you can find that by using RA minus RB. So this is the vector R. For this reason, your moment is simply defined as R cross F. So all you need to find is this position vector of this A relative to B, and then you perform a normal moment calculation with that force F. So by virtue of the definition that we learned, this means that the moment of this couple, since it has been reduced, we no longer think of the forces as two different forces. We are just looking at what? At the force F, or the positive force. Since the moment has been defined as such, then by magnitude we know it is RF sine theta, because the angle between these two is theta. Where is the theta? The theta, we can see it, it's defined there. So since we have our RF sine theta, then it's also equal to what? To FD. So in other words, the moment of a couple, you just look at the distance between the two lines of action of the force, of the forces that make up the couple. Then you already have your what? Your distance D. So by looking at, so this figure is just captioned, the moment M of the couple about O is the what? It's the sum of the moments F and the moments of F and minus F. So this is what we just did. So now, when we want to find moments that, or effects that are the same, we can actually find out that if you look at equation figure chapter 3, 27. Figure 327 is just showing you the moment of a couple, and it shows that it is equal to the product of F and D. That is what we had done in this equation. It's equal to the product F and D, and it is perpendicular to the plane of the couple and may be applied at any point of that plane. So that is the moment which we found out from there. Now, you can actually show that if you have a couple in a certain plane, this couple can generate a moment that is the same as another couple in a similar plane, but these planes are separated. So this is what brings us to the application of this concept of the couple. There's an example here just before we go to these equivalent couples. There's an example here on how to find the moment of a couple. So question 3.70 says, two 80 Newton forces are applied as shown to the corners B and D of a rectangular plate. Determine the moment of the couple formed by the two forces by resolving each force into horizontal and vertical components and adding the moments of the two resulting couples. So you've been given a method already to find this solution. Okay, so what are the data that we are given? We are given the forces. They are equal to what? 80 Newton. So I will write the magnitude because their directions are in a certain orientation. So we have that first piece of data. The second piece of data that we have are the angles at which they are aligned. So let me just call this angle maybe theta 1. let's call this one, it's the same magnitude, so it's also what? Theta 1. So let's just call it theta then. So what we want is to determine the moment of the couple formed by the two forces by resolving each force into horizontal and vertical components and then adding the moments of the two resulting couples. So let's give these forces some names, right? Let's call this force what? Let's call this force P is equal to 80 newtons. Let me just put the magnitude. Let's call this force Q, right? Let's call this force Q, just because they are pointing in different directions. So if we are to resolve, the method is to resolve into what? Into horizontal and vertical components. So the horizontal component of force P obviously points in that direction. So that would be P in the X. The vertical component of P points in that direction. That would be P in the Y. Let's have the vertical component of Q would be Q in the Y. Horizontal component would be Q in the X. So we now have the components. So for us to find the moment of the couple, let's go back to the principle. The principle just shows us that if we know the distance between the two, we can simply find the moment using the equation FD. So this implies that the moment of the couple in this case must be equal to, now I'm just using a magnitude because in the end I can figure out the orientation or the direction of rotation. So let's just look at the reference frame. Let's put X as that direction as we had done with the distances, and then that would be our Z-axis. So for us to find this moment, which is the total moment of the system, let's discover the moment due to the force P. The moment due to the force P is going to be we're going to have two forces, right? We're going to have this force P in the X, and we're going to have this force Q in the X. These two forces are acting at a distance of what? Of 300 millimeters. We are also going to have this force P in the Y and another force Q in the Y, and these forces are acting at a distance of 500 millimeters. By virtue of these forces having the same magnitude, you can actually see that your Px is an 80 sine 50. You can see that your Qx is equal to an 80 sine 50. Your Qy is an 80 cos 50. Your Py is an 80 cos 50. Okay, so by virtue of them having the same magnitude, your total moment can therefore be the horizontal moment generated by, the clockwise moment generated by the force Px. That clockwise, we can write it in the minus k, right? So that would be Px multiplied by what distance? That would be the distance. So this is the distance between the couple, which is now the Px and the Qx couple, right? So that's a Px distance is what? Is 300. So let's call this one the width. Let's call this one the length. So multiplied by the width. And this is in the minus k, right? Then we have the couple that is formed by this Q, which is in the what? In the Y, and this P that is in the Y. And we said, if we look at the magnitudes, they are both 80 cos 50. So these generate a what? An anti-clockwise moment. And by definition, remember yesterday we said the anti-clockwise moments are what? Are positive. So that would be a plus any of the two. So we will just take, let's say, Qx, right, multiplied by, right, we are now on the Y, so that's a Qy multiplied by a distance. So that distance for the Qy, you can see that the Qy is there and the Py is there, and the distance is what? Is the length. So in the end, you now have your total moment by considering the horizontal and vertical components of each of the forces. So that would cover your first part of the question. So let's just put it as that. And this is all in the k direction. This is all in the k direction. Because they say the moment, they did not say the magnitude of the moment. Now, they say use the result obtained to determine the perpendicular distance between lines BE and DF. Use the result obtained to get the perpendicular distance between the lines. So if we have the perpendicular distance defined as this D here, so that's our D there, right? And it is what? It is perpendicular to both the lines of action of the forces. Now, by definition in the second case, we said the magnitude of this moment is actually equal to what? Fd. So since we know that these forces are the same and these are 80, so this simply then results in the following. We already know this value from this calculation. If we look for the magnitude of that moment, right, we will be able to then say our D, which is the one which is required, right? We want to find the perpendicular distance. Our D is obviously then equal to your moment M over the force F. So which means you can find the distance from the what? From the moment. So basically what we are doing here was to take a case where we have two forces. We resolve them into the X and Y orientations or directions, just so that we can easily find a perpendicular distance. So when we looked at the P in the X and the Q in the X, they form a couple because they have the same magnitude but different directions. Their distance between the two was 300, so that's the width. So because they are the same magnitude, we can use our equation FD, and we append the direction of the sense of rotation generated by that couple as the minus k. So px in that direction, qx in that direction, tend to twist this to rotate in that direction. Right, the same applies for the reverse, where we have qy, which is pointed in the upward direction, and py in the downward direction, and their separation is the length. Then in the second part, you just use that. So, which means it is important to also think of decomposing the forces that make up the couple into rectangular, regular x and y, or maybe z axis forces. So that summarizes that example. The second principle on couples are what are called equivalent couples. So this figure here is a summary of equivalent couples. So it simply tells you about three equivalent couples. If you look at this first figure, figure A has a force of 20 pounds in the k direction, another force of 20 pounds in the minus k direction. And these are separated by a 6-inch distance between them. So, by virtue of these forces being parallel but at different directions, they generate a couple. So they generate a turning effect. So there is some moment due to these forces. So they tend to what? To twist. They tend to twist and rotate this, and you can actually calculate the moment being equal to Fd. You've got your F values there, and you've got your D given, so life is good. Then if you look at the second stage, you've got a 30 pound force rather. 30 pound force, 30 pound force. Couple by virtue of magnitude and parallel orientation and different directions. Distance between them, 4 inches this time. So what would be your moment? It's exactly the same as that. Sense of rotation, it's also exactly the same as what we had before. So it would rotate in the what? In the J direction. We also have the same forces that are acting at what? At another point. So this diagram makes it appear as if you can just apply, it doesn't matter where the forces are located. located. As long as they are forming a couple, then they will generate the same effect. So in the caption of this figure, we have some important information to extract. So it says a couple acting at the bottom of the box, that would be the first one, acting counterclockwise viewed from above. Yes, and then a couple in the same plane, and then a couple acting at a different plane, but the same sense. So the same sense here is the effect that you are observing when you look at this object, let's say from the top view, same object, top view, and so forth. So this is what the effect of a couple looks like. Now, the concept of equivalent couples can be proved. So this part intends to explain that when we have a couple that is acting on a body, we can actually figure out an equivalent couple. Remember this title, this study, chapters 3.4 and 3.3 and 3.4 are looking at equivalent systems of forces. So it's all about trying to decompose a system or a rigid body on which many forces are acting, trying to decompose it into a small or just a single force and a turning effect. So the concept of trying to figure out equivalence is exactly the objective of this lecture. So equivalent couples are now given in this example. So if you want to find an equivalent couple, you can actually test the couples this way. So the assertion is that if this rigid body has two forces that are acting on it, so we've got force minus F1 and force F1, we can prove that these forces, as long as in this case are coplanar, they are on the same plane, these forces will certainly be equivalent to that. They will generate a moment that is exactly the same as another set of forces that are oriented at that position. So how would one prove this? To prove that this system is equivalent to that system, you can think about it this way. These two forces are acting at their points. Let's just call these points. So according to what we see there, these are some points that have been removed. So let's just call these points as they are labeled in this part of the diagram, where we have point A and point B, point C and point D. So in part A of the diagram, the forces are acting on what? The forces are acting on point C and point D. Now, by the principle of transmissibility, we can just transfer force F1 to position A. We can transfer force minus F1 to position B, and we'll get the same effect. So we've got the principle of transmissibility to back us up there. So this is what is happening in part B, where we have the force F1 now acting at what? At position B, the force minus F1 on B, and then the force F1 on A. So if we are to choose components of these forces in directions of our choice, right? So if we are to choose components of these forces, the force F1, you decompose it to components. If you still remember in the first discussion, we said we can redraw a force into any direction of forces of components as we wish. So this is now a decomposition of this force F1 into two components. One component is called the force P, and it is oriented in the diagonal that passes through A and B. We are in the process of trying to prove that this system is the same as that. Then its other component, for it to make a parallelogram, will point in that direction, and it's called the force Q. The same applies for the force at F1, the force at B, which is F1. It will be given another component that is the same as, that is on the same line of action as the first one. And then we will have a minus Q in that direction to complete a parallelogram. If you look at this diagram, do you notice that if we were to use the principle of transmissibility, P and minus P are antiparallel, but they are collinear, so they add up to 0. So in the end, you end up just having a force Q and a force minus Q. And these two forces, Q and minus Q, have been derived from the same forces. They are components of the same forces. Fact that these components have what? Have vanished, have disappeared, simply means it was an effect of the principle of transmissibility. Now we are left with a couple, Q and minus Q, which will generate the same turning effect. If you then replace Q with minus F2 and you replace minus Q with F2, you end up having an equivalent couple. You end up having a system that was made from the first two forces but is oriented in a different direction on the same plane. So in this example, you can actually find a final couple that is equivalent to the same couple by on the same plane by using the principle of transmissibility and resolving the vectors into components. Similarly, you can have a couple that is equivalent to another when these couples are actually at different planes. Remember, this couple, we are saying it's the same as that couple, but these two different couples that we are defining as equivalent are actually sitting on the same plane. However, you can also prove that the couples that are sitting at different planes are also equivalent. So how can we prove that? You will notice that from figure A, we have couples, one couple at plane P1. If we are to use figure 2 and we are to construct a plane that is oriented diagonally. So it's a diagonal plane. That's a diagonal plane. So it looks slanted, right? So it is now a plane that is at an angle. We still have the force F1 on that plane. So we still have the force F1 on that plane, which is the negative F1. We also have the positive F1 on that plane, on the same point at which that force was acting. Now, one can carry out the process of proving this by creating a point at which no force acts, right? So if you introduce a force F3 and minus F3, you have actually introduced no force because these forces are pointing at what? Different directions, and they have the same magnitude. So they add up to 0. F3 plus minus F3 will add up to 0. So in the end, when you have this set up, you can effectively use the same forces that are at the axis of or at the intersection of your planes to create new forces that should generate the same effect as what you had in the beginning. So we still have, it's like a mirroring process. So we still have the same set of forces, but this time these forces are now seated on the bottom of these planes that are inclined. So by virtue of this force being non-existent because it's a zero force, then the effect that you found, look at this effect that you found from the couple generated by F1 and F3 on the same plane, and another couple generated by minus F1 and this F3 on the same plane, is the same effect that you will get if you have this F3, which was still here, and another force that is pointed in the different direction to create a what? To create a couple. So in the end, one can show that if we have a couple in one plane, we can generate a couple that is equivalent to the first in another plane of the same rigid body. So these are equivalent couples. So in the end, you will notice the following, that it does not matter where the two forces forming the couple act or what magnitude or direction they have. As long as these forces are a couple, it doesn't matter where they are forming the couple. What is important is the magnitude and direction of the couple. You can have a couple within a rigid body. That couple can be seated at the top of the rigid body. It can be seated within the rigid body at different orientations. That couple can be seated at different planes, but you will still have the same effect if you consider their magnitudes and directions. That is what is important for you to determine the couple acting on a system. So here you have an example of equivalent couples. So there are some shafts of a high-speed reducer unit. They are subjected to couples of magnitude. M1 is 15 foot-pounds and M2 is 3 foot-pounds. So the question is, replace the two couples with an equivalent couple, specifying its magnitude and direction. So here we've got our M1. So what is the data that we are supplied with? If you were to draw these couples, if you were to draw the directions of these moments, you can actually see that they are already conveniently located to these axes. So if we were to draw a free body diagram, we would just have some vector, and we would have some vector. Let's look at the directions now. This is rotating in the anti-clockwise, so it is a what? It is a positive moment. So we can say M1 is actually pointing in that direction because it is anti-clockwise about the z-axis. How about the x-axis? We also have an anti-clockwise M2, so that M2 is also pointing in the x direction. So our M1 is actually equal to, the magnitude is 15, so we've got a 15 foot-pounds. These 15 foot-pounds are in the k direction. And then for M2, we have an M2, which is the moment vector. So M2 is what? M2 is 3 foot-pounds. M2 is 3 foot-pounds, and it's in the I direction. So remember how to denote or how to deduce the directions from the rotation. As long as it is anti-clockwise about an axis that you are looking at from the top, right? This is the z-axis and you're looking at it. Then that anti-clockwise direction is the positive direction. So now we have those two moments. So how do we find the what? We want to replace the two couples with a single equivalent couple. If you want to replace the two couples, then it simply means that our new couple, which is the single equivalent couple, is simply supposed to be the first couple plus the second couple. So if you look at your vector directions, which are already given, it means you will actually get a couple that is oriented where? It will be oriented, there's an I and a J, these are all positive, so it will be oriented in this direction. That's your total moment, that's your total couple. Right, so those are equivalent couples. Addition of couples it follows the same sign. So addition of couples, this is now a principle on the behavior of couples. So if you have a couple, the question is, how do these couples behave? So if you are to add the couple, one couple to the other, how would you do it? So figure 3.32 is giving us an example of a setup that shows how to find the sum of two couples. So we have a first couple that is in its own plane, the couple created by the vector f2 and minus f2. We have another couple in its own plane P1 created by vector f1 and minus f1. So if we have these two couples, how can we figure out the resultant? So we have obviously at that point, a resultant force due to what? Due to force F1 and force F2. That is the resultant denoted by this R. The same applies. We've got a minus R due to minus F2 and minus F1. So if you look at R and minus R, do you notice that R and minus R are actually in their own plane? R and minus R are in their own plane. So because of that, they create a what? A couple. They are in their own plane, they are anti-parallel, and they are of the same magnitudes. So in the end, we have a what? We have a resultant. So this diagram is just showing. It's just showing us the moment due to what? Due to the first forces, F1 and minus F1. As you can see, F1 and minus F1 are on a horizontal plane. So obviously, their moment is going to be what? To be in the vertical sense. Then you also have F2 and minus F2. Theirs is looking or is pointing in the downward direction. So it looks like that. So if we are to look at the two moments, so we have this one which was upward on P1. We also have this one which is downward on what? On P2. Then the resultant is our resultant moment. So here we've got a caption that tells us that we can add two couples, each acting in one of two intersecting planes. The moment of the resultant couple is the vector sum of the moments of the component couples. So these equations are just summarizing the concept that our moment is just our R cross F, and since we have two forces 1 and 2, then by distribution we have the moment being total moment due to the force number 1, moment due to force number 2, and we add them up together so that the total moment is just a sum of the two moments. The total moment is a sum of the two moments. So that is basically the way you add couples. So this is more of a straightforward process where you're just adding your couples. Now, there is a special vector. There is a special vector called the couple vector. There is a special vector called the couple vector. So this couple vector is what is being introduced here. This couple vector is what is being introduced here. Now, the vector representing a couple is simply called a couple vector. A couple is a set of two forces. Instead of us drawing two forces all the time, you can just draw a vector called a couple vector. So in figure 3.33 part A, we are being introduced to the couple vector. So there is a couple here that is generated by two forces. So we've got a force F and a force minus F that are separated by a distance D. These two forces will obviously cause a turning effect on this plane, which is part of some rigid body. That the rotation sense of this couple is obviously in the anti-clockwise direction about the what? The y-axis. So if it is slanted, then it's about whatever axis is going through that plane. So here we have an axis through the plane, and we've got the direction of the what? Of the couple. So the couple vector is shown by this direction of orientation. This direction of orientation. If you notice, our moments do not actually have the what? The direction of rotation. But the couple vector is just showing us that we have a couple. Obviously, a couple will generate a turning effect. So it's as good as just writing the moment due to the couple. That is why we have this M is equal to FD. So a couple formed by two forces can be represented by a couple vector oriented perpendicular to the plane of the couple. So the couple vector is a free vector, so it can be moved to any other what? Any other points of application, such as the origin. So this couple vector is what has been moved now to the origin, so that it represents the couple that has been generated by those two forces. So in the end, you've got diagram D here, which shows you the components of that couple, because this is in 3 dimensions, isn't it? So we've got some X component, we have some Z component, and we have some Y component, hence the components of the couple vector. So here we have an example on how to interpret couple vectors. So we are given that shafts A and B connect the gearbox to the wheel assemblies of a tractor, and shaft C connects to the engine. Shafts A and B lie in the vertical YZ plane, while shaft C is directed along the x-axis. Replace the couples applied to the shafts by a single equivalent couple, specifying its magnitude and direction of its axis. It's a very important application, because while you want the wheels to turn, you want the engine to turn, you will end up making or generating some equivalent turning effect. So while you look at the design, you might not see what will happen to it. And this is very well applied if you have seen what happens with choppers when they are out of balance. The helicopter, when it's out of balance, you will notice that if there is no balance, we've got the rotation of the blade, we've got a very tiny blade at the back, which is more like a rudder. So you will notice that if there is no balance of those, you will see the chopper just it goes crazy. So basically here, now we can see how we can find an equivalent rotational system, an equivalent couple that is generated by different couples, because these ones are different. We've got some that are connected to the gearbox, and then for the wheel assemblies, and then another to the engine. So this certainly means that in the end there's some net turning effect. Right, so we need to identify these couples in the first place. So what are we given? So the data are as follows. If we are to sketch, we can see that at point A we have some couple. Let's call it MA. That couple MA has a magnitude 1200 foot-pounds. In what direction is this couple turning, right? In what direction is this couple turning? So this couple turns, we can see that if we look at the z-axis, it must have a component on this z-axis. It must also have a component in the what? In the y-axis. It must have a component in the y-axis. So what is its component in the z-axis? It's obviously that magnitude cos the angle. Let's call that angle theta is equal to 20. So it has a what? It has a component in the z-axis. If you look at that component in the z-axis, so this is in the k. If you look at that component, let's look at it from this direction. The rotational direction is still in the anti-clockwise. So this is actually a positive moment. This is actually a positive moment. It is a positive rotational effect that is generated by a couple. So we now have this as a positive value. How about this moment at B? How about this moment at B? By the way, moment at A must also have the other component. It must have the other component, which we said is in the what? Is in the y direction. So if it's in the y direction, then it's rotating what? If we look at it from the bottom, it will still have the same orientation of rotation. So if we look at it from the bottom of the y-axis, it will be rotating anti-clockwise to our view, right? So if it's anti-clockwise at the bottom of the y-axis, what do you see when you're looking at it from the top of the y-axis? We're saying this is the y-axis. At the bottom here, it's anti-clockwise. When you look at it from the top, it looks like what? It looks like a clockwise orientation. So in the end, you have a minus that 200 foot-pounds, and then multiplied by sine 20, let's just call that theta, in the what? In the j. Sine theta in the j. So using the same method, you can then find your what? Your MB, and then you find it using that magnitude 900. So you use your 900 foot-pounds. pounds. Let's just write that correctly. Foot pounds. So if we have that 900, let's look at it at point B. If you look at it at point B, its component in the z-axis, will be having a rotational direction in the clockwise. When we look at it from the correct viewpoint of the z-axis, it will end up having a what? An anti-clockwise orientation. So it will be a plus 900 cos theta. The same applies. You can do the same for the what? For the vertical axis. You'll have either a plus or a minus for the 900 LBFT sine theta. This one is straightforward. You can already see that it is what? It is a clockwise orientation about the x-axis, so which means your m at c is basically equal to minus the 840 foot-pounds in the I direction, minus 840 foot-pounds. So you've got the different moments there. All you need to do is to just find your resultant, which is basically a sum of each of those moments. Let's just call it I. So that is how you would find the direction of the resultant couple, the resultant single resultant couple. Right, so if you are to resolve into a force and a couple, so resolution into a force and a couple is a process now of decomposing. You've got many forces that are acting on this object. They cause, in the first lecture they were just causing some translation. Now they cause both translation and rotation, because these forces will be acting at different points. Let's just consider just one force in the first place, because when there are many, all we want to do is to find the resultant force and the resultant turning effect. But let's start from just one force. So as an important point, any force acting on a rigid body can be moved to an arbitrary point, provided that we add a couple whose moment is equal to the moment of F about O. What does that mean? If we are given some force F, right, acting at some point A, that force has a turning effect about O. So it has a moment about O. That force is located at position R. For us to replace that force so that we can find the resultant force and the turning effect, for just one force, all we need to do is to break the laws of physics, right? So we can just move this force, instead of us following the principle of transmissibility and moving that force along its line of action, sliding it, right? We deliberately move it to another point. So we've moved it from point A to point O. So this is our initial force, right? But because we moved a force to a point where there was no force, we need to counteract that that action. We need to counteract that action. So we then put at the same point, collinear, we put another force, which is minus F, so that in the end it appears as if we've not done anything. So these forces add up to 0, just in the same way we were trying to find an equivalent couple. So when we have a 0 force there, then it means our system is experiencing the same effect as though there was what? There was just one force. The rigid body experienced the same effect because there is one force there, and mathematically there is one force there. Having done that, we can now get rid of this force that was at that point, because our intention was to move a force to a location of our choice. So now that we've moved it to a location of our choice, and we've mathematically provided a counteraction to that action so that physically everything is still the same, then we can interpret this force and that force, which have now created a couple. This is the couple that has been created. This couple, F and minus F. Look at that D. So we have created a what? A new couple. This is F and minus F. So since we have created a couple, the couple has a turning effect. So we can replace that couple, this couple, we can replace it with a couple vector. We can replace it with a couple vector. For this reason, in part C of the figure, you now have an equivalent system, which is made up of what? Of the force which we transferred from point number A to point O, and the couple which was generated by the existence of this force and its counteracting force. So in the end, you now have a force and a couple that are replacing an existing force that was there on the system. So these are just steps on how to replace a force with a what? With a force and a couple. You are replacing one force with a force and a couple. At this moment, it might appear as if, why are we even putting a second force in what? In the couple? Why don't we reduce it to something simpler? It will work when we have 2, 3, 4, 5 forces. If you now have many forces that are acting on this body, then you can end up coming up with a resultant force and a what? And the moment resultant. That is the reason why this exercise is very important. Okay, so if you are to do it onto any other arbitrary point, remember we had moved our force to point O, right? Now we don't want to move it to point O. When we moved it to point O, we had this case. When we moved it to point O, we had that case. Now we don't want to move it to point O. We want to move it to point O prime. Point O prime. So if we want to move it to O prime, then the same applies, right? We had a force here. We have moved it to O prime, and therefore we should have a counteracting minus F. When we now have a counteracting minus F, it produces a couple with the first force. Then that couple is what we indicate with a couple vector. So as you can see, we've got a what? We've got a pull by the minus F and a push by the F. Then we have that rotation direction. So in the end, you can move a force to different points, as long as when you have moved the force to that point, you should remember to create a force that counteracts that action of the new force at that point. Then it forms a couple with the original force. So in the end, you've got this equation 3.49 that is derived from this part. So if you look at these vectors, I think it's more straightforward. The moment of the couple, that is the moment at MO prime. It's simply from the origin that we had. So we've got an R prime cross F. So this is our what? Our R prime. Remember, we said that our force is going to be like this. We are going to replace this original force by putting a counteracting minus F. So our couple is just this R cross F. It's just this R prime cross F. That is how we get our couple. So now we have a what? We have a case where the moment about O is now R prime cross F, and then our R prime can be interpreted from this vector triangle. So we know that for us to move from R prime in this direction, we need S plus R. For this reason, we have R plus S cross F, and then we have the Varinon's theorem to expand that bracket. So in the end, your moment about O prime is simply equal to the moment about O, which we found earlier, plus S cross F. So this is a derivation that just shows how you can resolve a force into a force and a couple. And this is just for one, so it's an ideal case. An example is shown, figure 3.82. So it says the tension in the cable attached to the end C of an adjustable boom ABC is 560 pounds. Replace the force exerted by the cable at C with an equivalent force couple system at A and at B, right? So you're given some points at which you need to find those force couple systems. Okay, so how would we find the equivalent force couple system? We have been given a point on which we should generate the new force. So if we are to draw our free body diagram, we've got our point A, we've got our point B, somewhere there, we've got our point C. At point C, we have the force T acting at an angle 20 degrees. Let's call that theta. We also have another angle here, which is alpha, right? Now that we have our dimensions and we can see our forces, we are also supposed to write our dimensions here. So let's just call it LAB, and then we have another LBC. So they are oriented like that. So for us to find an equivalent system at A, what do we need to do? Number one, we need to move a force. So number one, we need to move our given force to the desired point. Our given force to the desired point. So our T has now been moved to what? To point A. So there we have our T. So now that our T is at point A, we need to counteract that. We need to counteract that by doing what? By generating another force in the reverse direction. So number two, we have appended. So we have inserted, or we have put a new force minus F to counteract the motion, to counteract part one. That way the system remains as it were. We now have a force at the desired point A, and we have a couple that is created by T and minus T. We now have a couple that is created by T and minus T. So how do we then find this force? This force is simply T. So when they want us to state what force it is, then the force is actually T. So which means for part A, at point A, the force is actually T. So you can write its magnitude and direction according to the diagram that's given. How about the couple? The couple. What is the couple and how would you find the couple? So to find the couple, there are two ways, isn't it? We said our couple, let's just write it as M at A is equal to what? It's R cross T. R cross T, which R at C relative to A. R at C relative to A. That's how you would find your couple. Alternatively, you can resolve this T. You can resolve this T into this direction. You can resolve this T into that direction. Let's call it T in the what? In the normal direction. Let's call this the normal direction. So if you resolve your T into the normal direction, obviously here you would have the same. So all you need is to find the component of T in the normal direction. Then you multiply it by this distance LAB plus LAC. So we can write it as LAB plus LAC. B plus LAC multiplied by the T normal. So those are two ways to try and resolve a force into a force and a couple. So we have just replaced that system with a force and a couple. The direction of rotation of your couple is obvious, isn't it? We can tell that the couple is going to twist our system in the clockwise direction. So it's in the minus K if you are using this reference frame. Always note or always name or state the reference frame. So basically that covers your first part, chapter 3.3, where you're looking at the moments that are generated by a couple and how to replace a system with a what? With a force and a couple. Now 3.4 is now just looking at three different points along the systems of forces that you're now generating. So we have already seen how to reduce a system of forces. This time we're just expanding it into more forces. We saw one force, we're just expanding it into more forces. And then we have equivalent and equipollent systems. Equivalent and equipollent systems. So when we had the reduction process, then how can we then look at the system as a system made of just one resultant force? And how can we make that resultant force to be in such a way that if there is a turning effect, the same resultant force will represent the total force and the turning effect. So that's the reduction there and the range. Okay, so first principle is that you can reduce a system of forces. Now there are many. So it's exactly what we were doing before. We can now reduce any system of forces, however complex, to an equivalent force couple system. So how can we do that? Still remember, we said we move the force to our point of desire, the point at which we want. The whole idea is to just find one force. So obvious, all the forces must be moved to one position. So in this case, the origin is the point at which we want to locate our forces. So we take force A, force 1 from A1, we locate it at point A1. So let me just try to expand this to make it a bit larger. So it's now located at what? At the origin, but we provide a counteracting F1. So when we provide a counteracting F1, what we now have is this F1 and this moment, right? This couple. So this couple, as we can see, it will rotate the system in the what? In the anti-clockwise direction. For this reason, we have our F1 and we have an anti-clockwise direction for the rotation of this moment. So we have our first force and we have its couple, force couple system, F1 and M1. That is what we have there. The second one is F2. Again, we can move F2 to that point, provide a counteraction. So if we have our F2 and our minus F2, the F2 is now at that location, and then we have the what? The other moment due to F2. So the moment due to F2 is shown there. So generally, you will end up having a lot of moments and forces. Do you see that? You now have a lot of moments and forces. Good thing is all the forces are located at one point. Good thing is all the moments are located at one point. All the couple vectors are located at the same point. So if they are located at the same point, then we can add up all these forces. Let's add up all these forces. Add up all these forces. It's just now chapter 2, where you resolve the forces into the x direction, all of them, and you add it up. Y direction, all of them, you add it up and you get a resultant. The same applies with the moment. All the moments in the x, you add them up. All the moments in the y, you add them up and you get a moment resultant. This one is called a moment resultant. This one is called a moment resultant. So it's representing the total couple that you get, or the total turning effect that you get from that exercise. So the resultant force is just a sum of all the forces, and the moment resultant is just a sum of all the moments. And we found that we can also do it at another point, as we saw with the previous case. This is being done onto the origin, but we can move those forces onto any other point on the rigid body. So an example is shown in figure 3.37 here, where we are moving this system now that we have created, isn't it? We created it here. Now we are moving this whole system to a new location O prime. It's just the same, isn't it? It's just one force and one couple. We're just moving them to a new location. So now that we have that one force and that one couple at a new location, then we can, by the same sign, move this force to that point. Since we had that force here, we should create a counteraction there, and in the end we now have this new moment resultant about the point O prime, and it also has the same format as what we had earlier. So generally these are showing you, equation 3.54 is showing you that these moments have, these forces and moments are in X, Y, and Z components. If we were to just get some more information here, this text says once a system of forces has been reduced to a force coupled system at one point, we can replace it with an equivalent force coupled system at another point. So it's just telling us that carry out the first process, right? Come up with your total forces and put them at one point, come up with the moment resultant and the resultant force. By the way, it's very important for us to remember this. This resultant and the moment resultant is not the moment of the resultant force at point O. It's not the moment of the resultant point of force at point O. The moment resultant is, it was found through the summation of the couple vectors, right? So it was a summation of the couple vectors. Right, so the force resultant stays the same, but we have to add the moment of the resultant force about the new point to the resultant couple vector, right? So because we said we've got the moment of the resultant force, which is what? Which is when we moved this force there, we had the original force, and then we have the what? The counteracting force. So this is just explaining this equation. This is the moment of the what? Of that resultant, and then we are creating a new set. So this example here is just showing us how we can apply this concept. We've got a 3-meter long beam. It's loaded as shown here. So it's loaded as shown there. Determine the loading of problem 3.101 that is equivalent to this loading. So this is problem 3.101. So which loading is the same as what we have here? Which loading is the same as what we have here? What do we actually have here? We actually have the sum of all forces in the Y being equal to, so let's just call that the force at A and the force at B. So that's the force at A in the what? In the minus J, plus the force at B. These are all in the minus J. So those are the total forces, which means when you are looking for an equivalent system, we said an equivalent system must have a what? A force and a turning effect. So the equivalent system, whatever you look at here, the first thing you're looking for is a system that has a total force that is the same as these forces in the same direction. So that's the first one. Second one, you're looking at the total of the what? Of the moments. What is the total of the moments? You have to choose a point now, isn't it? You have to choose a point about which you are discussing these moments. So let's say you can say point B. Moments about point B. So you've got obviously these couples that already exist in the system. So you're going to add your what? Your 200 to the 500. Then, so let's just call it M at B plus M at A. So these were already there. So let me just maybe put a prime because they're already existing in the system. We've already been shown with the arrows, so we are not going to look for some forces that are generating these. Those are just what? In fact, we could actually see a couple vector pointing towards us. Now, we also have a moment due to this force FA. So we need to add the moment due to this force FA. FB is already at point B, so its effect is 0. So plus FA multiplied by the distance, let's just call it D. D is this 3 there. So basically you now have moments about B. Then you look for a system. You come again, you look for a system which has got the same total of the turning effects or total moment. So that summarizes how you would look for the loading that is equivalent. So that's the equivalent system. So now equivalent and equipollent systems are systems that respect these equations. So if we have forces that are equivalent, the sum of their forces, sum of all forces on the system of the rigid body and that of the equivalent forces should be the same. That's this part of the equation. And the sum of all moments should be also the same. When we look at the components, so this is where the equivalent systems need to be separated. If two systems of forces acting on a rigid body are equipollent, they are also equivalent. They need to have the same value in terms of the components. So in the x, we should have the same value of the components for the forces, the same value for the components for the moments. The same applies for the y and the z direction. So equivalence and equipollent systems are what are defined there. So how can we apply this principle when we were given all those equations, which are simply telling us that we can find an equivalent system as long as they have the same value for the moments and the forces in the x, y, and the z. So we are told in question 3.114 that there is a couple of magnitude m equal to 80 inch-pounds, and the three forces shown are applied to an angle bracket. The three forces shown are applied to an angle bracket. Find the resultant of this system of forces. Find the resultant of this system of forces. I won't do that one because I think you already know lots of you've worked out those a lot. Then calculate the points where the line of action of the resultant intersects the line AB and line AC. How would you find the line of action of that resultant where it intersects line AB and line BC? Okay, so you worked out your resultant. We've got some force in the downward direction. We've got some force in the upward at an angle. We've got another force on the left side. So you've got some resultant. So let's just call it R is equal to R in the XI plus R in the YJ, right? So I don't know which is positive or negative, so I'm just writing it in generic form. Just because the first part, I think you are used to this now, so you can do it. Now, how would you then locate the points of the line of action of the resultant on AB and on AC, on BC? So it depends with where this resultant is pointing. If it's like this, or if it's like that, or I'm not sure, right? So it depends with what you found from this resultant. So from what you found in the resultant and what you've also learned from what these moments, how these moments are interpreted, what we should know is that the sum of all the forces in the x is equal to whatever is the equivalent system. Remember, in our case, the resultant is the equivalent system. So whatever forces are acting in the x on the resultant should be the same as the forces that are acting in the x for each and every one of the forces that are existing. The same applies for the moments. So this means that the moments generated by the resultant, so let's say the resultant has an x component, isn't it? It is an x component. The x component of a resultant will be acting, let's say, in that direction. It's just an example. So let's say that is our Rx. If that is our Rx, then we should choose some point, right? Let's choose some point about which these moments are acting, because obviously we need some reference point. So if you choose some point, it can be point A, B, or C. So let's say you chose point C. If you chose point C, then your Rx will cause or will generate a moment Rx multiplied by, let's call this D1, right? Rx multiplied by D1. This is the moment in the what? In the anti-clockwise. So it's a minus Rx D1. So it's in the clockwise direction. Yes, it's in the clockwise direction. So it's a minus Rx times D1. So if it's in the clockwise direction about point C, then you look at, it must then be equal to. So we are now simply pulling out this equation. This was in the K, so actually we are pulling out this equation. The sum of all the moments must be the same. So when you look at the moments of each and every one of these forces about the what? About the point C, they should also give you this horizontal components moments. So basically you are now looking at each and every one of these forces, so whatever force and its moment about what? About C. So it will have some D from C, and then you add them up. So let me just put that, and then you will equate to that. That way you can end up finding what? D, and then you know the point at which this resultant should cross the section BC. Right. So further reduction can also be performed. So when we are discussing further reduction, all we are looking at are different ways of interpreting. This is where the project I was suggesting is located. So here we have concurrent forces that are acting at the same point. These would have, so this one, when you are reducing further reduction in 3D, is to reduce the many forces into just a single force. So what are the cases where we can find a single force? A single force is desirable, but it is not, it's not easily, you can't easily come across that. In reality, we always have a case where there's some turning effect. So you'll have a force and what? And a turning effect. But these three cases, you can find a what? A single resultant. So if forces are concurrent, right? So that's the first case. If forces are concurrent, all these forces are acting at the same point, then obviously they just add up, and then you end up having some resultant, which is components in the X, in the Y, and in the Z. So you can find a single resultant. If you have forces that are coplanar, right? So they are coplanar, they're acting in the same what? In the same plane. So you can, if they are in the same plane, you can just extend the lines of action, right? They will end up at some point where you can add them up to get a single force. You can find, just like here, they are all acting in the same plane. So even if they do not meet, right, these ones will meet. But even if we had another force that was acting in that direction, which would not cross with that force, but we can add all the X components, we can add all the Y components of these forces until we get a resultant. So coplanar forces can produce a single resultant. Parallel forces can also produce a single resultant. So as long as they are parallel, just like in the first case here, all these forces are vertical. There are two forces pointing in the upward direction, F1 and F3. There's a force that is pointing in the downward direction, F2. If you add them up, you will get maybe a net upward force. So this is a case where we can get a single resultant. Now the sum of all your forces is obviously supposed to be equal to 0. Equal to the sum of the individual forces in the X. Some of the forces in the Y give you a resultant in the Y, and so forth and so on. So equation 3.57 is trying to assist us to interpret what is happening in figure 3.38. So we can reduce a system of coplanar forces where we have an initial system of forces, and then where we can have an equivalent force coupled system at O, and then we can find, we can displace the resultant to get the same turning effect. So we have just moved all these forces, right? We've just moved all these forces to the same location so that we can get a single resultant. But because we had to work around using the previous method, we ended up having a turning effect. Now that resultant can be this only single force in the system if we move it in such a way that it is located at a point that generates the same turning effect as this turning effect. In that way, we can actually remove the MO moment resultant. In the second part, we are doing the same. We're just showing that this resultant can also be moved to any other point, as long as we will move it to a point that will generate the same turning effect as that moment resultant. So reducing a system of coplanar forces using rectangular components, that is what we are doing there. So from that figure, you can resolve the resultant into components xy, determine the x-intercept of the final line of the resultant, and determine the y-intercept of the final line of the resultant. So this you can actually use in the previous question, if you still remember the previous question. Right, so on this part, reducing a system of parallel forces. So this is where we have parallel forces. So reducing a system of parallel forces is a case where we have an initial system of forces, which is this one, right? Initial system of forces, equivalent force couple system at O. Obviously, all these will add up, isn't it? And then we'll have some resultant. But because each and every one of these forces was located a certain distance, let's say from X, so let's say we've got this distance from Z, we've got this distance from X, and we have only from Z and from X. So we will have turning effects about the X-axis for, let's say, F3, and about the Z-axis also for F3 on the other side. So the equivalent force couple system is what is being shown here. The equivalent force couple system is what is being shown there. It's obvious that these forces on figure 3.40a will only cause a rotational effect about either the X and the or the Y, in fact, and the Y and the Z components. They will cause rotation about the X and the Z axes. So basically that's why we see two moments there, M in the X and M in the Z, to represent a new equivalent system. So we have resolved this into components. We have moved R to point A, and it is chosen that the moment of R about O is equal to the resultant moment about O. So in the end, you can actually generate an equivalent system. So this is where an exciting project is located. This one could be actually something that you enjoy it's actually amazing if you do it well. So there are three children. They are standing on a 5x5 raft. If the weights of the children at points A, B, and C are 375 Newton, 260 Newton, and 400 Newton, respectively, determine the magnitude and the point of application of the resultant of the three weights. Determine the magnitude and the point of application of the resultant of the three weights. So how would you attempt this one? If we want to find the magnitude and the resultant point of application of the three weights, the first thing is we just need to find the net result, the net force, right? So obviously you can plot your data, you can collect your data, and your resultant is simply a sum of all the forces. In this case, all the forces are in the J, so we can just put this as the direction. So now that we have all our forces in that direction, we now know that, okay, the resultant force will be pointing down. Maybe it's there, maybe it's there, maybe it's in the center of the children, whichever way. So if you now have the value, or you now know the value of this resultant, now you can look at the total of the moments. You can now look at the total of the moments. So what is your moment resultant? It's simply the sum of the individual moments. So let's just call I for those three children. I is equal to 1 up to 3. So we can tell from this exercise that each of these children will generate, due to their weight, which is vertically down in the y-axis, they will generate a turning effect. So there will be a turning effect about the x-axis. There will be another turning effect about the z-axis. And as you can tell, all these turning effects about these axes are in the clockwise direction for the z direction, and it's in the anti-clockwise for the x direction. Now that you have found the total of the moments, if you have the total of the moments, this simply implies that you can now use this equation where you have your resultant on this left hand side being equal to the total of the individual moments. So which means you're looking at the resultant of, you've added them up. Now if the resultant is located at this point, the question is, what is its moment about the what? About the x-axis. What is its moment about the z-axis? And we should equate. When we have done so, this means that, according to the question now, we can actually locate the point of application of the resultant of these weights. Why? Because it is obviously located some d in the z and some d in the x. So which means if you have the individual children and their distances are already supplied. So if you have their individual moments, the only variable that you will not have is the d in the z and the d in the x. Otherwise, you will know the value of the resultant. So that exercise is also going to give you a method of locating the point at which that resultant is acting. So as a project, suspend a 3-point loaded plate. Just find some plate, some plane. Then if you can locate some beads or some weights onto that plate and use this method to find the location of the resultant, this means that you can put a pivot at that location and the system should balance. So this is a very exciting project where you can balance an object which is expected to fall apart. So you can make it remain in static equilibrium. Now that we have reduced a system of forces into a single force and a moment or a couple, we can actually also reduce a system of forces into a range. We can reduce a system of forces into a range. What is a range? It is basically, okay, we can see a good example there where we have a system of a force, downward force, and a couple that is coaxial with that downward force. That is a range. So the system of the method of getting the resultant, we already know it. The method of getting the moment resultant, we already know it. So we now know that this is the general couple that is running the system. So if we have that, you can use the projection theory. You can actually project your moment resultant onto this axis of the resultant. You can project your moment resultant onto this axis or onto this resultant. This is what will have happened with that part of this equation. It's a projection of the moment. You are in the process of generating a range. So if you project that moment onto the resultant, then you already have them coaxial. This is what then takes place. So in the end, you have a projection of the moment resultant, which is now M1, which is the projection of the moment resultant onto what? Onto R. That is what we have on this part. But for you to maintain the equilibrium status of the system, you will, this one had a component, isn't it? This one had a component, so you will need to define that component. As long as you have projected M1 onto R, then you need to also specify your M2. So this M2 is obviously at 90 degrees to this range. So reducing a system of forces to a range is a simple process. The general force system is reduced to a single force and a couple vector. but not perpendicular to each other. That's the only difference. These are collinear. So resolving the so this is the first part. They are not perpendicular to each other. In part B, now we are resolving the couple vector into components along the what? Along the line of action of the force and perpendicular to it. So this is just a projection onto R, and this is the other component of this MOR. In the end, you actually have a range. So now by applying the method that we used earlier, we can actually end up moving this range to a convenient location which generates the same turning effect as this M2. If we do that, we now have just a single range. If we do that, we have a single range. So part B is resolving the couple vector into its components. I think that has been seen, M2 and M1. And this text says they are resolved into its components along the line of action of the force and perpendicular to it. Then moving the force, that's C now, moving the force and collinear couple vector, which is the range, to eliminate the couple vector perpendicular to the force, to eliminate this M2. So in other words, we want to leave the system with the same turning effect, but all we want is to draw or to obtain a range. So that range then must be located at point A for it to generate the same effect as for M2. So if you check in your text, you will notice that in figure 3.42, by finding the position vector R that locates any arbitrary point on the axis of the range, you can then define the axis. So we are just defining the axis at which we have the range. Our position vector R is just telling us the point from some origin. So that's the axis of the range and its definition. And the pitch of the range is defined, so that's another property of the range. It is defined as the ratio of what? Of the moment M1, which we projected onto R as a ratio M1 to the vector R. So in the end, you now have this definition, and if you substitute what we had earlier on, this projection calculation, you will see that you can actually draw your pitch of the range from this equation where you have the scalar product and the square of the magnitude of the resultant force. So what you're just doing in this exercise is to find an equivalent system. And in this case, the equivalent system must be a range. So in this case, you want to replace a what? A range shown with an equivalent system consisting of two forces that are perpendicular to the y-axis and applied respectively at A and B. You want to replace this range. So we already had some other system before in the introduction, which showed that you can actually generate a range. This is like a reverse process. So they are telling us that they want us to replace this range with an equivalent system consisting of two forces that are perpendicular to the y-axis. So perpendicular to the y-axis applied at A and B. If they are perpendicular to the y-axis, they have to be what? At right angles. So let's just say maybe there, that's at right angles. So that could be one of the forces. We could also have another one, obviously, so it has to be like this, so that it is also at right angles to that. So you can obviously now generate your forces, a force at point B in the Z direction, a force at point B in the X direction. Right, having those forces, you already have the method, right? You already have the method. You know that these forces, if you've got another one there, according to, they want A and B, it's obvious these two forces should add up to that. And these ones should add up to what? To 0. Because we do not have a resultant force in the X direction. So this process is the same as what we had before. All you want is to work backwards to find the forces that you can use to replace what we have there. The first suggestion, which was saying you can then add the forces to get R, is for us to get the magnitude of the forces. How about to find the actual locations of the forces? Then we need to look at how to generate this turning effect So add up all the turning effects that you're getting from this diagram. Add up all the turning effects until you get the force. So in the end, this exercise was there to make use of couples, force couple systems, and systems of forces. Couples, force couple systems, and systems of forces. In summary, your force couple systems you are looking at a couple in the first place. What is a couple? It is generated, or it's made of two forces. These forces must point in different directions. These forces have an associated couple vector. The couple vector is always drawn like a normal vector with a line to show that it is representing a couple. So that couple vector, when we look at the replacement part, we can replace any system of forces. Just move the force onto the desired location, create a counteracting force, so that you can end up with the force at your new location and another couple. Then all that can be put together to actually find the location of a point at which you should apply the resultant, so that in the end you can find an equivalent system. So this summarizes what we are studying in this chapter. I just hope that you are able to go through the exercises, and I think it will work out for you. So let's meet in chapter 5 when we will discuss the next phase of this module. But otherwise, we are done now with our basics of forces, equilibrium in 2D, 3D, forces and their moments about a point and an axis, and then force couple systems, wrenches, and replacing a system of forces with a force or a resultant force and a resultant couple. That summarizes today's work. I hope you will have fun as you go through this discussion. Okay, have a good day and all the best.